Hello, Jeep here. Today I want to talk a little bit about programming and how it applies to non-programmers in terms of understanding how programmers work, what they're doing, and what they're thinking. And this talk is not about learning how to code. This is not a way to learn how code works or anything like that. And in fact, one of the things I'm going to talk about is how programming is not code. So let's just jump right into it. So like I was just saying, programming is not code. If you look in the upper left here, you'll see some code. And what code is a language that lets us communicate with computers and give it a set of instructions to tell it what to do. And just like any other language, maybe you think in your head sometimes in English or in your native language, sometimes programmers think in code. And so just as another example, guitar tabs are not the same as playing guitar. And in the bottom left, we have some kind of quilting method. But anyway, that's just a chart that shows how to knit something, but it's not the same as knitting. And if you look in the bottom right, this would be like the records of a chess move. And so this is also not the same as playing chess. These are just different languages for expressing the concepts in those types of fields. So what is programming? Well, like I said, it's telling the computer what to do. And like I said, sometimes programmers will think in that language. They'll see the world through the eyes or filter the world through the language of code. And outside of code, we have to decide how to tell the computer what to do. And this is usually much more like big picture, bird's eye view, very structural. And it's about figuring out how different parts of everything will link together and work together. And often in teams of people, how those people will both be able to do different parts of the program and fit them together. So there's a lot of planning involved, and there's a lot of, we sometimes just call it architecture, but it's a more conceptual term. And then another major thing that programmers do is we break down problems into smaller parts, and we break down those smaller parts into even smaller parts, and we keep repeating that process until all the parts are small enough to actually solve. And if you look at this diagram, you can actually follow the arrows backward. We are given a problem like, hey, I would like some brownies, and we have to work backward to figure out, okay, well, we have to cook those brownies. And to do that, we have to make some mix. And to do that, we have to have some ingredients. And some of those ingredients have different parts in terms of how they're prepared or how they're measured. So that is kind of what programmers are doing. I should mention at this point that this talk is not intended to be comprehensive. This doesn't cover absolutely everything about programming. These are just some of the things that I felt like were interesting to talk about, and hopefully you'll find it interesting too. So how do programmers think? So this is a really great post that I've seen going around that's pretty funny, where basically if you ask a game programmer to, make a giant demon bust out of the ground and lava fly everywhere, they're like, yeah, sure, no problem. And if you ask them to put a scarf on the player character, then they go, ooh, I don't know about that. That's going to be really hard. And I think sometimes people look at programming as just complete magic or almost a black box. And I just want to kind of explain the inner workings or the logic when you ask a programmer to do something and half a second later they have some response about how easy or hard it is. Those aren't just like pure guesses, and they're not just an answer out of nowhere, and they're not an answer to make you happy or make you mad. Programmers, when they think about a problem, they actually are considering lots and lots and lots of details, and in their mind breaking down all those individual parts and thinking back on their experience and thinking ahead to what types of things they'll need to solve. And all of that goes into a formula that eventually comes out into an answer like, oof. So, what are all these calculations they're doing? Well, the first thing is we sort of look at a problem, we ask, how can this be represented with numbers? Computers really just understand numbers, and so to do anything with a computer, you have to first break your problem down into numbers and represent all things with numbers. So the next thing we think about is, what is the pattern in the problem we're trying to solve? Like, often each part of the problem isn't one very specific thing with one very specific solution for each of the individual parts. Often most of the parts are similar to each other in some way, and we try to figure out how are those parts similar to each other, because the more similar things are, the more we can sort of take one solution and apply it in many different ways to lots of different problems. So we also look at how much detail is needed when we're trying to figure out basically the numbers that we need to represent something. Can we do it with 10 numbers, or do we need 100 numbers? Do we need 1,000,000 numbers? Exactly how small or how specific do those numbers have to be, or how general can they be? Because sometimes by using more coarse measurements, like if you only use 5 numbers to represent something, it can be much, much cheaper to develop, and it can be much, much faster to like run in the actual program. So yeah, we are always thinking about exactly how much detail do we actually need, and how much can we fake? How much can we skip? So just like I was talking about before, that amount of detail is often part of trade-offs, where we think about, if we solve a problem using one solution, it might be good in some circumstance, but it might actually be a bad solution for a different circumstance. And then the opposite. Sometimes if we go with solution B instead of solution A, it's better in some situations and worse in the others. And there are often these opposites where doing one thing well means you do a different thing worse, and exactly the opposite. We also think about, what are the edges, meaning when we're solving this problem, what are the very, very extreme cases that we're going to get? This could be, for example, when a form says, please enter your name, and somebody puts in their name and it's 3,000 characters long. How do we deal with this case? What if somebody puts no characters in the what is your name box? How do we deal with that case? So yeah, we're always kind of thinking about, what are the very weird things that people will try to do, or what are the like very extreme pieces of data that we might have to deal with, and plan ahead so that we don't cause future bugs. So I want to break down those things I was just talking about into an example. So let's look at some pans. And these pans, the first thing I said we're looking at is, how do we represent these using numbers? Well, like I said, there is a very, very simple answer to this. There are 9 pans, so let's say we just number these pans 0 through 8. We have pan 0, 1, 2, 3, 4, 5, 6, 7, and 8. Those are our 9 pans. And I'll explain why we use 0 in a later slide. But so that's fine, but what if they say, now we want a 10th pan and an 11th pan? Now you're getting to the situation where you're not reusing your solution for each of those pans. Each time you add a pan, you have to come up with a new solution. So like I said, we're going to look for the patterns. So what are the patterns here? We have some pans have lids, some don't. Some heat up fast, some heat up slow. Some are very deep, some are very shallow. They're different colors. They're different shapes. We have a square pan, we have sort of an oval pan, we have round pans, and then the size, just in terms of like the actual diameter, is different per pan. So if we look at the patterns of pans, we can try to make a solution that will solve all pans of all these different varieties. So the next thing is we try to figure out how much detail is needed. So just looking at these examples, I could basically say, well, there's 3 different lids. There's the metal lid, the glass lid, and the no lid. There's maybe 3 different heat rates. There's 3 different depths. There's 3 different colors, 3 different shapes, 3 different sizes. These are very, very approximate figures. But if you say that there's 3 of each of these things, now we can represent 729 total possible types of pans just by using different combinations of these values. And if at some point we decide we actually need more detail in the types of shapes, like let's say there's 7 different shapes, well, we can make changes to just that axis and still have that work for all the other types. Okay, so what are the trade-offs? I'll give you two examples here. Let's say you have a shop with a warehouse in the back where all 729 of these varieties of pans are. And if somebody comes into your shop and wants to buy a pan of a specific type, you have exactly that pan already. It's there. It's ready to go. Or how about the opposite? You have no warehouse in your shop. You only have a catalog, and everything is custom order. When a customer comes in, they tell you what type of pan that they want. They give you exactly what lid, heat rate, depth, color, shape, size that they want. You then submit an order to a factory. The factory builds that exact pan, and then you deliver that pan to the customer. Now, one of them is very, very fast, but you need a large warehouse. The other one is very, very slow, but you don't need a warehouse. So if you look at those two things, there's positives about some and negatives about it, and then the opposite, there's also positives and negatives. So these are the kinds of trade-offs we're looking at. And last, we're looking at what are the edges. And again, by this, I mean, what are the extreme examples? So what if we have 0 as one of these values? So for example, the heat rate. What if the heat rate of a pan is 0? Does that mean it never ever heats up? What if the depth is 0? Does that mean it's a skillet? Is that possible? Okay, how about negative? What is a negative depth of a pan? This is probably an error. I don't think we should actually allow negative numbers. Okay, what about a maximum? Is the pan allowed to be 1,000 miles tall? I don't know. Probably not. I think we should have some limit and say that maybe the maximum height of a pan could be 6 inches or so. Okay, what about the negative max? So what is the lowest possible value? So maybe we do allow negative values, but what is the absolute minimum that we will allow that makes sense? So these are just some examples. There's often other types of cases that you need to think about and plan ahead for, but usually some of the first test cases when you're representing something as numbers is 0, negative, max, negative, max. Do these still work? So then we actually skipped over one of the most important steps. You've figured out exactly how your pan is going to work, and then your client tells you, oh, actually, these pans aren't for cooking, they're for weapons. So another really important question to ask is, what are the specifications? What are the requirements? What are we actually trying to build? Because if you don't ask this question, you can build completely the wrong thing. In this case, none of these things matter. The lid, the heat rate, the depth, the color, the shape, maybe the size. Really, all we care about is how much damage does it do? How fast can you swing it? Does it break after a certain number of hits? All of these things are completely different numbers than if we're using it for a different purpose. Okay, so the rest of this talk, I'm just going to point out some of these sort of jargon words, and I'm going to explain how they work really, really quickly, but then I'm just going to get into a practical example of kind of what they mean and how they're used. So here we have abstraction, interfaces, and refactoring. These are words that programmers use a lot, and they have very specific useful meanings, so I'm going to kind of explain what they are. So here what we have is a diagram of a cell phone charger, a very, very simplified diagram. And this is something that we can call abstraction. Abstraction is taking something and simplifying it so that you can see just the absolute most important critical parts with kind of all the details stripped away. And often this is about taking some real world object or some larger problem, and again, simplifying it into a way that we can represent with numbers and diagrams and connections. So the next thing is interfaces. And so USB is one example of an interface. And when you connect USB to your phone, you can see there's all these different types of connections, and each different connection is sort of a contract that's saying the thing that connects to this side of it is designed to work in a very specific way. And as long as there's an agreement about exactly how this connection is going to be used, then any phone that uses USB-C can use a USB-C connector, and any phone that uses USB micro can use that connector and understand exactly how it works. So often there are many different types of interfaces, but these are just some examples. Okay, so we have these interfaces, but it's really complicated and they're all competing with each other. And so that's when we start thinking about refactoring. And refactoring is where we take a system like this that has basically too much going on, and we delete a bunch of it and replace it with something more simple, more elegant, that solves all those problems in a more similar way. So one thing that programmers love more than writing code is deleting code. It feels really good. And this is sort of what we're talking about when we're talking about refactoring. And here is just an example of, we have a wireless charger. You put the thing on it and it charges. And again, everything that understands this interface can use it. Doesn't mean that it's backward compatible with all phones, but it's a way to simplify a bunch of problems that existed with previous phones. So our next set of jargon is isolation, optimization, and complexity. So let's just jump into an example. So one day I came home and the Instant Pot wasn't working. And my wife said, well, there's a dent in the side and it's not working, so I think maybe we should buy a new one. So I looked at this and I said, well, actually there's been a dent in this Instant Pot for months, maybe years, so I don't think that's the problem. Let's isolate the problem. So isolation. So what this means is trying to figure out where the problem is coming from by removing what the possible problems are. So I'd already sort of mentally subtracted the dent, but we don't know if that's the problem or not. So the first thing I did was I plugged the Instant Pot into a different outlet. Hey, guess what? It turned on. So it's not the Instant Pot that's broken. The next thing I did was I plugged a different device into the outlet that the Instant Pot was originally plugged into, and that device did not turn on. So now I know the problem is not the Instant Pot, the problem is the outlet. That's isolation. It's finding where is exactly the problem. Okay, so the next thing is optimization. So often when we're solving a problem, we want to figure out what is the fastest way that the computer can perform some set of operations. So in this case, I'm actually the computer, and the set of operations I need to do is figure out how to make this outlet work. Well, one very, very efficient way that I could solve this problem is to say, let's actually just not use that outlet. Let's plug in the Instant Pot into a different outlet and pretend this never happened. It's a very fast way to deal with this problem, but it comes with a bunch of downsides, obviously. It doesn't actually really solve the problem. And a lot of times, optimization does look like that, where we're basically just saying, let's pretend this didn't happen. Let's do something completely different. Let's fake it. And as long as it looks like things are working, then we're okay. Well, then there's other solutions. Like, what if I want to go watch a tutorial video and learn what the steps I need are? Or what if I go to the fuse box and just flip all the switches and then flip them all back on? What if I go to the GFI switches, which is the little red button that's kind of like in the middle of bathroom outlets that you have to push in sometimes? What if I need to push all those in? So what is kind of the most efficient way that I can figure out what's going wrong with this outlet and solve it? And then complexity is when you solve a problem, often we think about what are all the steps that you need to do to solve it and how complex are those steps. So a very, very simple, low complexity solution is I have a repairman on speed dial. I call him and I say, hey, please come fix this outlet. And then I stop thinking about it. But a more complex solution could be, what if I build my own personal custom robot that can go and press all the GFI buttons for me and flip all the fuse box buttons for me? You know, it's probably very overcomplicated, because how am I going to get the robot to move around the room without knocking everything over? And how will I get it to know exactly where all those switches are to flip? So this is probably not a great solution, but that's sort of what we're talking about when we're thinking about complexity in terms of how much work is it to make this work. So next on the jargon list is more related to source control, which is kind of how do we share files between each other. So these words we hear a lot, which is push, submit, or commit. These are kind of the same thing. They're a little bit different, but the distinction is not super important for this talk. We also have pull and sync, which are kind of similar. Merging, programmers talk about merging all the time, and I'll explain why that is. And then code reviews. So as an example, let's say I'm planning a trip two people are planning a trip, and we both take a piece of paper, one of these travel planners, and we're going to go into separate rooms, and we're going to write down where do we want to go, what days, and on those days, what do we want to see and do. And after we're done, we show our itinerary to the other person. This is what we could call pushing or committing or submitting. This just means, hey, let me show everybody what I did. This is what I came up with. So I came up with Siesta Key in Florida, and we're going to be there between these days, and there's going to be dinner and drinks and fishing and sunset boat ride and things like that. That's my form. So now when I pull or sync, it means I want to look at what the other person did. So looking at somebody else's itinerary, what they wrote, that's pulling or syncing. Now comes the merge. This is where things get tricky. So merge is kind of like a compromise where we're looking at these two different travel planners and we want to figure out what is the same and what's different and how do we reconcile, like how do we compromise on those differences. So here you can see we picked the exact same dates, so there's no conflict. Merging is perfect there. Destination, we both picked Florida. The other person picked Miami. I picked Siesta Key. Honestly, there's not a huge difference, and maybe I was being more specific. So when we try to choose between these two things, we might make an argument one way or the other about which is better, but let's say we go with Siesta Key. Next, we look at all the individual things that we chose. So on Monday, we both picked dinner and drinks. Yay, no conflict. On Wednesday, they picked zoo and I picked fishing. So we look at this and say, well, even though there's a conflict here, actually they wanted to do fishing on Thursday. So what if we do fishing on Thursday and then we also do the zoo on Wednesday? Then everything is actually okay there. And then Friday, I wrote down dinner and drinks. They wrote down bar hop. Well, maybe we want to do, again, some sort of compromise between these and say, let's do dinner and bar hopping instead of just saying dinner and drinks. And then I wrote down sunset, boat ride, and they had nothing for Saturday. Maybe we should just do the boat ride, or maybe they really had a good reason that they wanted to do nothing on Saturday and we should remove boat ride. But in the end, we merged these two together, and that is the merging process. Okay, and then code reviews. I think sometimes people get confused about what a code review is, but I would explain it sort of like a second opinion. So for example, if we're both writing these lists, before I submit my list, before I show it to the other person, what I want to do is I want to get a friend to give me a second opinion, to look at my list and say, oh, actually I've been to Siesta Key and I have some recommendations for things that you had not considered because you've never been there. Or maybe they say, actually, the person that you're going on a trip with, they told me that they get seasick really, really easily. You should probably not do the boat ride because they're not going to enjoy that. So doing a code review is before you submit code, having somebody look at the code with you and decide if they can see possible future problems that you hadn't considered. It just gives you another fresh set of eyes, and it's very, very useful. That's what a code review is. All right, so this is our last set of jargon. We have and, or, zor, or xor, depending on how you want to pronounce it. We have not, zeroth. I promised I would talk about zeros a little bit. And then semantics and pedantics, basically why are programmers like this? So this question, do you want ketchup or mustard, is kind of a little bit weird, and we actually have to be more specific about what question we're trying to ask. Let me give you a different example. Let's say you order a burger and they say, do you want fries or onion rings? Well, the ketchup or mustard question, you can have ketchup and you can have mustard. When you ask, do you want fries or onion rings, you're not really allowed to answer both. You can only have fries or onion rings, not both. And so this type of or is what we call XOR or ZOR, and it stands for exclusive or. Exclusive or means you can only have this or you can have this, but not both. So the way programmers use the word not is often used as part of a question, where the question is, if there is not something, then something else. So for example, if there's not regular fries, I don't want onion rings, and I don't want sweet potato fries. I actually only want regular fries. So if there's not regular fries, then I want nothing. And speaking of nothing, like I said, we talk about 0 a little bit. When programmers count, we often start our counting with 0, not 1. So instead of saying 1, 2, 3, 4, 5, we say 0, 1, 2, 3, 4. And the reason for this is that 0 is a very, very useful number because 0 also represents nothing in a lot of cases. So often when we're thinking about how to represent something with numbers, 0 is the default case or the empty case or the error case or the nothing case. So if I'm representing, do I want ketchup or mustard? 0 might be no ketchup, no mustard. 1 might be just ketchup. 2 might be just mustard. And 3 might be ketchup and mustard. Okay, so the last part about why are programmers so fixated on semantics and why are they pedantic about things? Well, it's because communication errors can cause real problems that can be like very, very expensive. So in our onion rings and fries example, if somebody says, do you want onion rings or sweet potato fries? I might choose either one of these thinking it's a vegetarian option, but if they don't tell me that these are fried in pork fat, then that could be a problem for me as a vegetarian. I'm not a vegetarian, by the way, it's just an example. But it's kind of the same when we're working on a real problem. If there's some piece of information that we forget to communicate with the people we're working with, or if we use a word to explain how we're solving something and it's the wrong word or it's not exactly the correct word, then there can be misunderstandings, and these misunderstandings can lead to unknown problems in the future. All right, so here's what I hope you take away from this talk. First of all, programming is not just code. Second, estimation has a process. We think about how much something will cost or what is the right way to solve it, and in the blink of an eye, we might have an answer, and you might not like that answer. Everything you see around you, everything that you do, in some way or another can be broken down into numbers, and it's all about figuring out how to represent those numbers in the most useful way. And last, when we're solving problems, we need to take a very holistic approach. We look at the overview, what are all the large pieces and how do they all connect together? And we also look at the very finite, minute details and break them down. And both of those at either end of that spectrum matter completely. Anyway, that's it. I hope this was useful for you. I don't usually do a lot of programming talks on my YouTube channel. I don't actually do a lot of English content on my channel, but yeah, if you thought this was cool or useful, just let me know in the comments. If you thought this was a waste of your time, let me know in the comments. It's really useful for me to hear some feedback. And yeah, if you thought this was cool, feel free to subscribe if you want. If you don't want to, that's cool too. See you later. Have a good day. Bye.